more or less taken as intuitively known. That if the two systems A and B have different level of hotness, they are not equally hot, then if you place an adiabatic wall between them, so the adiabatic wall, it typically could be a thick layer of wood, asbestos, or thermocol. In that case, system A and system B can continue to have different level of hotness or coldness. On the other hand, if you place a diathermic wall, so our concept of calorie was this, that there is something called heat which has to be transferred to an object in order to heat it up. So that was called the caloric. So then, a wall which allows that to flow through is a diathermic wall. An example could be a thin sheet of metal. A wall which doesn't allow the caloric to flow through is an adiabatic wall. Could be a thick layer of wood or thermocol. So then, two systems are said to be in thermal equilibrium if they are connected by a diathermic wall. And then came the zeroth law of thermodynamics. The statement you probably would be familiar. Two systems in thermal equilibrium with a third are in thermal equilibrium with each other. So So let us say I have two systems A and B which are not in thermal equilibrium with each other. They are separated by a diathermic wall. But both of them are in thermal equilibrium with a system C. They are separated from system C uh, by a diathermic wall. So separately, both system A and B are in thermal equilibrium with system C. Now, once it has reached that equilibrium, if I isolate it from system C and bring them in thermal equilibrium and then place a diathermic wall between A and B, I'll find that A and B are already in thermal equilibrium, no heat transfer occurs. So it means that once they are in thermal equilibrium, some property of the two systems is same. So if a certain property of A is same as that of C, and of B is same as that of C, that property must be same, since A is equal to C, property of A is equal to C, and property of B is equal to C, property of A and property of B must be equal. So all it tells you is, if certain objects are in thermal equilibrium, they all have a common value of a certain zeroth law. So all the zeroth law tells you is, when a variety of a number of systems would have the same degree of hotness, which we call the temperature. But then it tells you nothing about comparing two systems which are not at the same temperature. So then, if I know that a system B is hotter than a system A, the two are not in thermal equilibrium. If I connect them by a diathermic wall, there would be a heat transfer occurring from one to the other. Then how much? Let us say system A is hotter. So if I connect them by a diathermic wall, caloric flows from A to B. I still do not know um, how to quantify how much hotter is object A compared to object B. So then some definition has to be found. So then people found that certain measurable properties change with temperature. We found that a phenomenon called thermal expansion often occurs. A certain liquid, if it is heated, its um, um, volume increases. So then people said, okay, if I take a liquid in glass, so this may be mercury or some other liquid, and uh, there is air above. In that case, if I heat it, both the liquid and the air would try to expand, but then the air is more compressible. So therefore, the liquid would displace the air, compressing it in the remaining space. So the column of liquid would rise. So this gave us a way of measuring temperature. People said, okay, let us now define two reference points. One could be melting ice, and the other could be boiling water. And let me do both experiments at atmospheric pressure. And let me dip the thermometer. Let me dip this thermometer in both. Let me dip this thermometer in both. Then the thermometer, I can mark out the 2 points where the liquid column extends, both for the melting ice and the boiling water. So then let me call this 0 degrees centigrade, and let me call this 100 degrees centigrade. So I mark those here, divide it equally, and then I have a temperature scale So if I dip it in some other, a tank of water which is not boiling, so I dip the thermometer in here, and let's say the column comes out here. So I have marked out, so I have divided this scale, so I can now read out the value from here and call this the temperature. So I now have a way of measuring the temperature of any arbitrary system. The difficulty arose that depending on what material I choose for the liquid, I would get a different value, which meant that the expansion is not uniform for all materials. So then people said, okay, people observed that a gas in the limit of low pressure going to zero. So if I take a gas at sufficiently low pressure, and then uh, instead of measuring the expansion, they said, let us measure the pressure. So the gas in a certain volume, its pressure was it was kept at constant volume, and its pressure was measured using a manometer. So that was taken as a definition of temperature. Later, the definition was changed, but originally that was the definition of temperature. That the pressure of an ideal gas at very low pressure, that defined the temperature scale. So you would place it, that bulb of gas, you would place it at melting ice, take that as the definition of 0 degrees centigrade, put it in boiling water, and take that as the definition of 100 degrees centigrade, and then divide the pressure scale equally between these two intervals, and that defined temperature. Now, following the syllabus, let me just mention certain terms. We spoke of uh, physical properties and thermodynamic properties. So, how many thermodynamic properties are there? So, for an ideal gas, you know that it satisfies the relation So normally you would have an nRT or an MRT depending on whether your gas constant is, so N would be the number of moles, and then the gas constant would have to be in terms of per mole. In engineering calculations, more often we take the gas constant in per mass. In that case, it would be MRT. So then the gas law would be PV is equal to MRT. If I divide by M, then I would have capital V by V. So I define my small v to be capital V by M. So then this is the volume per unit mass, which is called specific volume. So here I can see that the gas constant is a constant. I have a pressure, a temperature, and a specific volume. These are properties which are not related to the gross position or velocity. So these are thermodynamic properties. And I have three properties, but they are not independent. They are connected by this law, and therefore I can choose only two independently. Now, turns out that this is true of most pure substances. So, if I specify what is the pressure, what is the temperature, the specific volume gets specified. And then, if I have specified the temperature, The other properties like internal energy and further properties which we'll define like enthalpy and entropy, those also get defined. So essentially, there are two degrees of freedom for a pure substance in one phase. So I require two independent values in order to specify the thermodynamic state of a system. So the property values, their tables, etc., are given in terms of two independent variables. If I have two phases in equilibrium, then my number of degrees of freedom decreases, and I can choose only one. So if I'm thinking of water, I can have it at any pressure, any temperature. So at atmospheric pressure, I could have it at any temperature. But then, if I require water and steam in equilibrium at atmospheric pressure, then I can have it only at one temperature. So then, the number of degrees of freedom gets restricted if I have two phases in equilibrium. So then, I can choose only one. If I have three phases in equilibrium, then I talk of the triple point, then even that degree of freedom vanishes, and I can have that only at a certain pressure and a certain temperature. Now, the triple point is rarely of concern to engineers. If you are dealing with a boiler, we are dealing with water and vapor in equilibrium. So there, if it is saturated, I require one coordinate. So it could be either pressure or temperature. So properties of water are saturated water. So water which is in equilibrium, where the liquid is in equilibrium with vapor, those are tabulated either using temperature or using pressure. So two tables exist. The
Sir,
properties are available.
sir, like someone is waiting in the lobby. So,
Oh, thank you. Thank you. Hi. So then uh, the properties are known for saturated steam are tabulated. There are two sets of tables, one in terms of temperature, one in terms of pressure. Uh, Whereas for superheated steam, if you have steam and steam alone, in that case, you could heat it further beyond its saturation temperature, and at a certain pressure you could have it at various temperatures. So those properties are tabulated in terms of pressure and temperature. So thermodynamic properties, the properties we commonly require are temperature, pressure, temperature, pressure. So many of these concepts we still haven't introduced. We'll introduce them as we go on. But what we have to remember at this point is that for a single phase, uh, two independent properties have to be specified, and then everything else is known in terms of those two properties. If I have two phases in equilibrium, then it's only one thermodynamic property which can be specified. Then the syllabus specifically mentions thermodynamic equilibrium. So a system is said to be in thermodynamic equilibrium if it satisfies, if it is in mechanical equilibrium. So by mechanical equilibrium, we mean there are no unbalanced forces either between system and surroundings or between parts of a system. Thermal equilibrium is when you have heat transfer. So that heat transfer occurs because of temperature differences. So two systems are said to be in thermal equilibrium if they are at the same temperature. So thermal equilibrium is when there is no temperature difference between the system and the surroundings and between parts of the system. Then we also have chemical equilibrium. So if you have two substances which can react, and although there may be no forces between parts of the system, there may be no temperature differences, but a reaction can proceed between two substances if um, the reaction laws permit. But in our engineering thermodynamics discussion in this course, we'll not be dealing with reacting systems. So chemical equilibrium, we'll take it for granted that that condition is satisfied. So if all these conditions are satisfied, the system is said to be in thermodynamic equilibrium. And when the system changes from one equilibrium state to another equilibrium state, we'll also assume that the process is a quasi-static process. So that at any point of time, although it is moving from one equilibrium state to another equilibrium state, at any point in between, it is almost in equilibrium with itself. So it is practically in equilibrium during the process of moving from one equilibrium state to another. In the intermediate stages, the deviation from an equilibrium state would always be small. So having discussed the preliminaries, let us now come to the main point of discussion. We said our emphasis here is on open system. So open system is what we have not been trained to deal with when we studied physics in school. But engineering systems, quite often, like you saw for the turbine, that was an open system. So how to analyze the behavior of that is what we need to learn. So do we have to learn it right from the beginning, or can we use our knowledge of laws as applicable to um, closed system in order to analyze an open system? So this is done using something called the Reynolds transport theorem. So I mention this name because the course, the syllabus specifically mentions that Reynolds transport theorem has to be covered. But if you look up the books on thermodynamics, none of the books on thermodynamics mention something called the Reynolds transport theorem. So Um, uh, this is something, this is a term typically used in fluid mechanics. So the discussion also we can find in books on fluid mechanics. So this discussion, I'll take it from the book by F.M. White, Fluid Mechanics. So this is the book which I said I'll follow for fluid mechanics. So it's convenient taking the discussion also from the textbook which we intend to follow. So here, now the terminology, as I said when I was discussing system, the terminology, everybody doesn't follow the same convention. So the terminology also has certain differences depending on which book you're reading it from. So when we discuss system, we said systems could be of various sorts. Systems could be completely isolated, which have no interaction with the outside world. Otherwise, they could be closed systems. In thermodynamics, a closed system can have work transfer across the boundaries, can have heat transfer across the boundaries, but cannot have mass moving across the boundaries. And then you could have open system where you also have mass moving across the boundaries. So a system could also have mass moving across the boundaries. Now, the terminology used in the uh, fluid mechanics book by F.M. White is a little different. So he uses so he talks of system versus control volumes. So according to what we discussed, this would be called a closed system, and this would be what we have called an open system. So now the what the Reynolds transport theorem says that we have various thermodynamic properties and various laws. So we have various conservation laws. We have the conservation of mass, we have the conservation of momentum, we have the conservation of angular momentum also, say if you are dealing with a turbine. Then we have the conservation of energy. So we also if you uh, examine at a final level, there's a distinction between conservation of energy and conservation of mechanical energy. So then there are various conservation laws, and all these conservation laws we would, so if a system has no force acting on it, the linear momentum would be conserved. If on the other hand, if a force is acting on it, the rate of change of momentum, linear momentum of the system is equal to the force. That is what we know from the laws of mechanics. So then, that law as it applies to a certain uh, a fixed mass of material. So if I consider a certain object as it is moving, the um, rate of change of its linear momentum is equal to its force. Now, if I want to apply the same law to a system which has mass flowing in and flowing out, how do I do it? So then, the same question I would have regarding energy also. So it seems uh, we have certain laws of nature which we have been taught um, what we know what they are when they are applied to a certain fixed mass of material. Now we want to apply those laws to a certain system, which we could call either an open system or a control volume, where I have mass flowing in and flowing out. So if I have mass flowing in and flowing out, how do I apply the conservation of momentum or the conservation of energy to that system? So I could have a rocket where mass is flowing out from the rocket engine, and I want to calculate what is the acceleration. So it would be inconvenient tracking the outflowing gas. So I would like to put my control volume enclosing this. So now I have a control volume where I have mass flowing out of the system. So then if I have mass flowing out, how do I apply Newton's laws to this system? Similarly, if I have a turbine, I have hot steam flowing in, high pressure steam flowing in. The steam undergoes expansion and then leaves at a lower pressure. So a convenient control volume would be this. Now, from first law of thermodynamics, we know that if there is no change in the energy of a system, the heat flow into the system is equal to the work done by the system. So, energy in one form is flowing into the system, and energy is flowing out in another form. And the two must be equal if there is no energy change inside the system. Now, that applies to a fixed mass of material. Now, here, if I have material flowing in and flowing out, how do I apply the first law of thermodynamics to this system? So then, here, my question is, what happens? How do I do the calculate the rate of change of momentum? So, what effectively is the force acting because of gas flowing out? So, the momentum conservation consideration is what I'm interested in over here, and here I'm interested in the energy. So I may be interested in different physical properties, but the question is the same, that I know the laws as they apply to a fixed mass. How do I apply them to a control volume where I have material flowing in and flowing out? So I could have, in general, a certain property. So let us say B is a certain property and beta is the specific property. So this is B per unit. So beta now let us look at the conservation laws. So when I say system, this system is in the FM White convention, that a system means a closed system. So the mass of a system remains unchanged. So this is what I know from Newton's law. Rate of change of linear momentum is equal to force on the system. Rate of change of angular momentum is equal to torque on the system. So all these you know from mechanics. This also I assume you know because the plus 2 level course covers the first law of thermodynamics. We'll discuss it later, but then you're already familiar with this concept. So the rate of change of energy of a system is equal to rate of heat transfer to the system minus rate of work done by the system. So all of these laws apply to a certain amount of material. So if I have a closed system, I can apply the laws directly. But what if I have an open system? So then, so I have two derivatives: the rate of change of B for a system and the rate of change of B for a control volume. So so the Reynolds transport theorem, the aim is that if you can do it for an arbitrary property without bothering whether that property is um, mass, momentum, angular momentum, or energy, or mechanical energy, or entropy. At the moment, we just say it is a certain property which is an extensive property and which is associated with a specific property which is The specific property is the property per unit mass. So if I have such a property, can I relate the rate of change for a system to the rate of change for a control volume? Then, if I have a relation between the two for a system, I can apply these laws. The laws, as we know them, apply to a system. So I can apply it to a system. Now the system, the rate of change for a system, if I can relate it to the rate of change for a control volume, then using that relation, I can find out what is the rate of change. So I can then apply the laws to a control volume. So the Reynolds transport theorem actually establishes a link between this and this. So let's say at time t, so let us say I have a control volume. Now that has nothing to do with time. For simplicity, we could, when I was first discussing it, I said that a control volume could be moving in space, but since we are trying to cover both thermodynamics and fluid mechanics all together in one course, the stand I'll take is, let us not introduce more complication than we require. So when I'm deriving the Reynolds transport theorem, I'll assume that my control volume is fixed. So if it is not fixed, then you'll have to follow this derivation and extend it for whatever requirement you have. So for simplicity, I'll assume that the control volume is fixed in space. So since mass moves across the control volume, the notation I'll adopt is opposite of what this diagram I've taken from a book on fluid mechanics by Streeter. So he denotes the control volume by a continuous line and the system by a dotted line. But then I'll follow I'll follow the opposite convention, because the control volume is a surface across which mass can move. So let me denote that as a porous boundary, dotted line, and the system boundary by a continuous line. So the control volume, as I said, remains fixed in time. At time t, let me take my system boundary to coincide with the boundary of the control volume. Now, let me go to time t plus delta t. The control volume remains the same. The system, let us say, I have my control volume is in a space where I have fluid flowing in this region. So let us say the fluid is flowing this way. In that case, after certain time, my system would have moved. So this will be my system boundary, and my control volume boundary remains unchanged. So then I can mark out three regions. Region 1, the region which belongs to the control volume, but from where material flows out during the interval delta t. So if I talk of the system, region 1 is part of the system at time t, but it's no longer part of the system at time t plus delta t. Then region 2, which remains in the control volume um, and the system, both at time t and time t plus delta t. And a region 3, which does not belong to the control volume, but which is included in the system at t plus delta t, because material which was in the control volume at t has moved out to this region during the interval delta t. So then, if I see the system, what is the property of what is the property value in the system at time t plus delta t, then at t plus delta t for the system, I'll have to add up the contribution from 2 and 3. Whereas for the control volume, I'll have to add up the contribution from 1 and 2. So then, if I apply to 2 and 3, I can calculate what is this quantity. If I add up for 1 and 2, I can calculate this quantity. Now, if I can estimate what is the value of the physical quantity B in region 1 and 3, then I can relate this derivative to this derivative. So this is what we need to do for the Reynolds transport theorem. So we'll do it in the next class. And talking of schedules, today is August 13th. Next week, okay. Okay, next week, Wednesday is 18th. It is Institute Foundation Day, so probably they'll have some program, and that is why they have notified that classes should not be held. 19th is a holiday for Muharram, which means our next class would be on 20th. So 20th is when we'll meet next time. By then, I hope the roll list would have stabilized. So we'll meet again next on 20th. So whether to meet through Google Meet or through MS Teams, that I'll let you know through email before the next class. Okay, so we'll stop here.